the section, which is important. The 11.8 is a combination of different types, or it's, the only thing to do is just going through the different kinds of integrals and just do examples. So that's the only way to learn it. So the first one is the integral of the type 11.91. So it's an integral with the type integrating some periodic function that in terms of sine and cosine or whatever, and integrating over the period and 2 pi. Obviously, if it is not in 2 pi, then if it's periodic, then you just normalize it to this form, and then you can use whatever the formula is. So so f usually as I mean many integral will be defined as real integral, but if it's not real, then obviously it can be compact also. It still work. But if it is real, then make sure that your answer is also real, because there's nothing complex here if S is real. If you get something complex out of it for a real function f, then yeah, you have done something wrong. Okay, so so the idea is to make it like a complex integral, and because we know the Euler relation, and especially because we want to get just the cosine and sine, so we define as complex. I mean, we require the complex number going through a unit circle, so it's e to the I theta. And now the only thing to do is just do transformation variable, just change a variable, to change theta to z, and then you just follow the usual way of changing variable. So you want to get a d theta out in terms of dz, so you take the derivative of that. You get I e I theta d theta. Okay. And then whatever sine theta, cosine theta is coming from the Euler relationship is cosine theta. Sine theta. Obviously, if it's negative, then it becomes negative, and we solve for cosine theta. This is going to have e to the I theta plus e to the minus I theta. In this case, we substitute z back to here. Whatever 2z plus 1z. Okay, so that's straightforward. And the 2i minus minus and the 2i minus. Okay, so now you have everything. Cosine, sine, go into this, the argument of the function. D theta is solved for D theta. Yeah, one more step is here. Because you want in z, D theta be dz divided by IE to the I theta, which is minus I divided by z dz. Okay, so everything in terms of z now. D theta go into here, sine theta, and cosine theta. Okay, so that's just straightforward. I mean, supposedly you don't need to remember the formula. You just divide that in 2 minutes. Okay, right. So just do the usual change of variable. You just know the idea. That would be fine. I mean, memorizing formula is okay, but don't memorize the wrong formula. The idea is okay. Now, once you do that, you just change that to the integration in on the complex plane, because z, and you integrate now theta from 0 to 2 pi over a unit circle. This is 1, this is I minus I. Then obviously, whatever f, now it's f, because you have z, the f divided by z is your integral. So if you write it more explicitly, I will be, you have a minus I here, f is z. This is a unit circle C. Z. Right. B, C, 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 and F. Now, in terms of the argument change to in terms of these function, which is now in the general form. So now you look at the integral f over z, and where are the singularity inside? If they have isolated, if the function f over z has some isolated singularity within the unit circle, they might have some outside also, but you only count those inside the unit circle. And obviously that would be, we have minus I times 2 pi I sum over the residual. Okay, and that would be the answer. Okay. I mean, even this step you don't need to memorize. Just know the idea is change it to a loop integral over a unit circle, and that would be the rest is just analyzing the function f over z and see what the singularity are, and then evaluate all the residues. Okay, so next thing, just do an example to illustrate that. So let's do the first example. There are two examples, but I'll do one because of time. So this example. Okay, 8.1. I is d theta over plus a cosine theta. Okay, and there's a condition a is less than 1. The magnitude a is less than 1. It's not specified a is compact or real. Or so, so that is a complication. Hopefully, it means it's real. Otherwise, there are some uncertainty over the location of the poles later on. So I mean, according to your text, and yeah. This one, yeah. This one, the minus I is coming from here. Minus I. The 2 pi I mean, this is residue of f over c. If you like, you can multiply minus I inside and call this the function minus I times f over z, the whole function. But it's just the same. I don't know what the textbook say. The textbook, the formula of the textbook is, yeah, the textbook has a minus I. I'm writing in the same way as the textbook. This minus I is from this change of variable. Is it okay? All right. So now go back to here. Assuming A is real, it's just that it could be positive, negative. And obviously for real A, if A is greater than 1, then you get into trouble along the path 0 to 2 pi, because cosine theta take all the values from 1 to -1. So whether and when actually a is even positive, it's also trouble if a is greater than 1. So the magnitude has to be less than 1 in order that the denominator is not 0. If it's 0 along the path, then it's singular, and the integral is not well defined, then you get into trouble. And so then we just follow the rule here. You change that to -I and half integral over the unit circle, and dc over c, and then f is 1 over this factor 1 plus a cosine theta is 1 plus a, and cosine theta is this one, equals 3 over 2 c plus 1 over c. All right, okay, I forgot that in remarking. So that's general form. So, but if you see something like sine n theta, cosine n theta, then all those are also covered. If it depends on sine n theta, cosine n theta for some n is integer, then it also cover, because one way to do it is use those trigonometric formula, express sine n theta, cosine n theta into powers of sine theta and cosine theta. You know those formula. Another way to do it is just make sure that you can follow exactly the same process. Like if this is to the power n, then there's the n here. So cosine n theta would be c to the power n plus 1 over z to the power n. Okay, so it's just following the same way, and you can cover those dependencies also. Yeah, I mean, this is just one common thing, and obviously there are other similar situations that you can just use your algebra to just express, basically change the variable to see that you get you'll be able to apply this method. Okay, and now the rest is algebra, because now you multiply z inside, what you get is 3 terms of z plus a over 3 c square plus a over 2, right? 3 terms. And obviously you want to solve it, and you, like what I said last time, you want to factorize it. Usually z minus the root of this function, so z minus something, and there's a quadratic equation, quadratic expression, so it should have 2 roots. So in order to write down the standard form, you pull out a over 2 power of the integral. So you go minus 2 y is a easy. Becomes z squared plus 2 over a plus 1, right? And then formally you can now write it easy c plus, there will be 2 roots in c plus, c minus, and the c plus and minus would be just given by your quadratic, the solution for the quadratic equation, which you memorize. That should be 1 over 2, and b squared would be minus b, right? Minus b here, so minus 2a plus minus b squared minus b squared minus 4ac. B squared is 4ac minus 4a. Right? That's the formula. Okay. Then you can cancel the 2 with the numerator. So I'm getting too low in the bracket. So just erase that. This becomes 1. This becomes 1. This becomes 1. Right? Yeah, 2 roots of c plus or minus 2 roots. So now now you need to figure out whether they are inside the circle. Now you use the fact that the a is less than 1. So so this one would be the magnitude is this is less than minus 1. I mean because a can be positive, negative, or the magnitude of this term is greater than 1. Yeah. Then it depends on the sign of a. Then one of them will be greater than 1 because you plus that in addition to that or minus that. If it's negative minus that would be even outside. And then if it's positive plus sign will be outside. It depends on the sign of a. Then to be specific, why don't we just say a? Because that doesn't really matter. It's just it's just one way or the other. Did the text specify the sign of a? No, not really. Wait, did I get the one? Minus 1 over a minus. You pull out 1 over a. Minus a squared. Yeah, right. Yeah. If the text would write it like you factor 1 over a out, that would be a better way. Factor 1 over a out, this becomes 1. 1 minus a squared. A squared is less than 1, so that's fine. So the factor is greater than 1, right? And so if you have something that's the magnitude is greater than 1, then it would be outside. So minus 1 will be the magnitude of minus 1 minus this factor will be greater than 1, and divided by something smaller than 1 will be outside. So this one will be outside. Minus sign will be outside. Only the positive sign is inside. It's okay. So, and one more, I mean, that because of the form, so the c plus times c minus is this term. So one is greater than 1, the other will be less than 1. C plus times c minus is 1. Okay, so so you see that so there will be 1. C plus is somewhere, assuming they are real, there will be that will be on the real axis somewhere. So C plus. Actually, it depends on a. Well, doesn't matter. It depends on the sign of a. If a is negative, then you plus C minus. So you only have one residue. That's C plus. We got to.
Can't both be outside.
You can't both be both C plus times C minus is 1. Do you see that? You factor this one into here. You compare the term, compare the constant term. The constant term is coming from C plus times C minus. Okay, the C plus times C minus is 1. So if one has a magnitude greater than 1, the other has a magnitude less than that. Okay, okay. Okay. So, I think let's go back to me because I'm outside the scope. All right, so let's just write out the answer. And these are simple poles, right? And for C plus only, so the answer would be I would be, 2i over a. Now you multiply by 2 pi I, and the residue is multiply the factor c minus c plus to cancel this factor in the denominator, and take the limit z goes to c plus. So it would be 1 over c plus minus c minus. Right? And c plus minus c minus is cancel this term. Plus minus minus get you a factor of 2, right? 2 over a. And I times I is minus 1. Cancel with that. So you have 4 pi over a here. And then 1 over c plus minus c minus is 2. And there's a 1 over a here. So a 2 and minus a squared. There is 2 pi a squared. Is that true? You followed it? let's see if I got it. Wait. 2 pi over square root 1 minus a squared. Yeah, that would be it. Is it too quick, too fast? Do you follow all the steps?
Did you clarify the residue portion again?
This to calculate it from here, right? Now you know that you want to calculate the residue of C plus, which is this factor, and you use the formula. Last time we said how you calculate residues. For simple pole, the answer is just multiplied by the same factor C minus the pole. In this case, C minus C plus. So you multiply the integral, which is this, the whole thing, 1 divided by this. You multiply C minus C plus. You cancel this one. And the final form, you substitute C equals to C plus, or actually take the limit of C equals C plus. So that becomes C plus minus C minus. And the integral will be this residue multiplied by 2 pi I, and the rest is just the coefficient in front of the integral, which is this one. And now you just evaluate C plus minus C minus using this form, the quadratic solution, and get to here, and the answer. Okay. All right, so that's the first type. It's okay, the first type. So basically, it's fairly straightforward. And there are formulas if you want to memorize. If you don't remember all these formulas, just figure it out again. Just using usual way of doing change of variable. And remember, you finally evaluate that the integral in the unit circle on the convex plane. Okay, and then use a residue theorem to figure out what the integral is. All right.